Well, hello there. This is Craig Hane, or Dr. Dell. And the title of this video and essay is a new number system for a science math model. And I'm doing this in December of 2019. Now I want you to treat this video just as food for thought by an old high school math teacher, me. This is not going to teach you anything that is particularly true or new. It's just ideas that I've had, and just to stimulate you. I think that when we think about life and math and so on, sometimes we need to sit back and sort of philosophically think about it and just ask ourselves, what's it all about, and why are we doing it, and are we doing it right? Could we do something better, and so on. We have something we call the real number system, which you've learned about in our training. And I won't tell you what it is. I'm sure you know all about it from our tiers 1 through 5 training. And of course we use our number system both for counting things and for measuring things. And yet we want to keep our number system fairly simple from an axiomatic viewpoint. So what that meant was we had to allow for measuring things that are arbitrarily small. Now, let's suppose that 1 is a unit of measurement for something, and n is a very large number. Then 1 over n will measure something, and since n can be arbitrarily large, then the something we're measuring can be arbitrarily small. But now the question from a science viewpoint is this real? We call them real numbers, but is this really real? We're sort of assuming that something that we can measure can be measured with infinite precision. When we say a line is, 1 unit of length long, we mean exactly 1, not a little more, not a little less. Well, what I want to do is I want to give you some ideas in this video for maybe a new number system we could create that would assume that there's something so small that there can be nothing any smaller. You have to think about that a little bit. Is it possible that there's a limit to how small something can be? Well, let's just think of a line, and suppose we have a finite set, and it's one-dimensional. It's a line of what I'm going to call pixels. I'm not going to call them points. I'm going to call them pixels. Now, a pixel is like a point, except a pixel has a non-zero size. It's not zero. And so there's only can be a finite number of them on a line of any given length. Now we can count them with natural numbers, and so we can assume that there is a large finite number of them, and it can be as large as we like, but let's avoid the word infinity. Let's don't think about an infinite number of them. Let's just think that we're interested in a science model, and of course nothing in the real world we know of is infinitely long or infinitely numerous. So let's consider that we have a set capital N of these pixels. Now capital N is a number, and if we have a set of n of them, then we can say, well, what would a set of 1 over n of them be? Like if n is 100, what would be a set of 1 over 100 of them? Well, it'd be 1 pixel. And of course then we can have m divided by n of them too. In other words, if we had a set of 100 pixels, I can say what would be 3/4 of the set. And you'd say, well, 1/4 of the set would be 25, and so 3/4 would be 75. So you can have what we call rational numbers, m over n of them. But we may not be able to have 1 over x of them if x is arbitrarily large. You have to stop and maybe think about this a little bit. I was thinking about it, in fact, this morning early. Let's say that we have that the number n is the number 17. That's a natural number. Then we could say, well, we can have 1 over 17 of these objects, and that would be 1 of them. We could have 3 over 17, and that would be 3 of them. But here's what we couldn't have. We couldn't have half of them. What? Well, 17 divided by 2 in the ordinary number system we use is 8.5, but there is no 8.5 pixels. There's either 8 pixels or 9 pixels, but there's no 8.5. So 17 over 2 in this new number system, if we're not allowing arbitrarily small things would either be an 8 or a 9. So what we might want to do is define 17 over 2 in this new number system as, I'll just put it in brackets, 8 comma 9. I'm just saying this is something to think about conceptually. Maybe we would do this. Mind you, I'm speculating here. I'm imagining things. This is not the math that we teach today. And by the way, when you invent new math systems, and when our ancestors did, they would do this sort of. This is heuristic reasoning. This is intuitive reasoning. Now, what we might want to do is we might want to create some new measuring system. And since these pixels would be very small to compare whatever we're measuring, we could do that. This would be true if the pixels, for example, are what we call Planck length in size. And I'll tell you a little bit about what that is later. We're measuring things that sapiens like to measure. We're measuring things of our size. Planck length is extremely small. So if we're going to measure something, let's say these pixels are Planck length, which is extremely small, and we're going to measure something that we're going to call 1 unit of length, which will be n pixels long. Remember, you got a line here, and you got these pixels lined up on it. So we're going to say that 1 unit of length is n pixels, and n is a very large number because these pixels are very small. Well, then we would say that a half of u of 1u would be p comma q, where p plus q was n, and p could be, q could be p or p plus 1. If n was even, p and q could even be even. Okay, let me give you an example. NO2 may not exist in this number system we have, but p and q would, where p is less than n over 2 and q is greater than n over 2. And we could define the square root of a number a very similar way. Now, I told you that, let's look at 17, the square root of 17. Now, the square root of 17 in the world we normally live in is somewhere between 4 and 5. Well, remember now we're talking pixels here, so it could either be 4 or 5. So we're going to say it's in parentheses 4 comma 5. That's kind of the best thing we can do. And you say, well, that's what is this nonsense, right? Well, let's suppose we're talking about really, really large numbers. In other words, n is a really, for the unit of length, is really large. Well, then the square root of n would be p comma q, but p and q would be very large adjacent numbers. So, for example, in this new number system, the square root of 1 million would be 1,000 comma 1,001. P would be 1,000 and Q would be 1,001. Pretty large numbers. But suppose that n was a 1 with 12 zeros, okay? 10 to the 12th power. Let's see, that's a trillion. Then the square root of that trillion would be 1,000,000 comma 1,000,001. That would be P and Q. Okay? In other words, we're not allowing ourselves to have arbitrary precision. What we're doing is we're avoiding what I call infinity. In our real world, we can expand any number as an infinite decimal, but in this world, we're only going to have finite decimal expansions. We're avoiding what are called irrational numbers. Let's consider the Pythagorean theorem. Let's go now to 2 dimensions, where we now have points in a plane that are ordered pairs of these numbers we're talking about. And let's say that we have a right triangle and the sides of the right angle are 1 unit long. What's the length of the hypotenuse? This is what our Pythagoreans considered. Now let's suppose that these pixels are very small. And so let's say that 1 unit of length is 10 to the 30th power of pixels. 10 to the 30th power. Well, the hypotenuse from the Pythagorean theorem is 1 squared plus 1 squared, take the square root, so it's the square root of 2. Well, if this 1 unit length is 10 to the 30th pixels, then the square root of 2 would be 10 to the 15th power, comma, 10 to the 15th power plus 1. In other words, you're not talking about the kind of numbers you normally think of. Now, this may or may not make sense to you. You might want to think about this as I have, and I don't know if I expressed it very well. But the big question is now, could we create an axiomatic system that would deal with these kind of numbers, where you had a limit to the size? In other words, there weren't infinitely small numbers. There was some smallest possible number. Could we create an axiomatic system that actually did that? Well, suppose that we could. I don't know that we can, but let's say we could. There's lots of axiomatic systems. Then if we could do that, we'd have a number system that could avoid infinity. And infinity, it seems to me, is one of the things that presents all sorts of difficulties for our current scientific math models. Now, what I've just said to you is probably going to appear nonsensical to most mathematicians. But so did Cantor in his time. When Cantor in his time came out and started he was really the father of the modern concept of infinity, if you want to think of it that way. He really dealt with it in a rigorous, axiomatic way and created what I've talked about in other videos about infinity. And at the time, mathematicians thought he was crazy. They thought the ideas were nuts. They couldn't see any application of it to the real world. And I'm going to go down to the bottom of this PDF that I'm using as notes and talk about some of those mathematicians. When Cantor came out, as I said, there were mathematicians that didn't like the idea of infinity, the way Cantor did. And probably the most famous was Leopold Kronecker. Now, he made a famous statement that gets quoted a lot. God invented the natural numbers, and all other numbers were invented by man. Aristotle didn't believe in infinity. And I just heard recently of another guy named John Penn Maybury at the 20th century that didn't think it's right. So there may be things there that you can study. Well, one of the things that we talk about in math today is infinite series. And you've studied that in tiers 4 and 5. And suppose that we have a system where 1 unit of measurement is n pixels, but now we're talking about a finite system. Well, that means we don't consider any fraction 1 over m if m is greater than n. Well, we might say that 1 over n is 0, 1 if m is between n and 2n, but then we might say for any larger m, 1 over m is just 0. Now that just absolutely eliminates infinite series the way we know them. In other words, if you can only consider numbers of a certain small size, then all infinite series become finite series. And a converging series that in modern math converges, I believe, would still be converging in our current system. But a series like 1 over n, the harmonic series, 1 plus 1 half plus 1 third plus a fourth, that wouldn't exist, because beyond a certain n, 1 over n would be 0. And so it would only be so large. Now, how large would depend on what we decided our smallest pixel was. Does this make any sense in our new axiomatic system, which we might create? Like I said earlier, what would it be? I don't have such an axiomatic system. I haven't thought that much about it. This is food for thought. This is kind of heuristic, speculative thinking. Suppose that our real world, the world we live in, what we think of as space-time, is actually discrete. and I think some scientists believe this, there's a thing called Planck Length. 1.6 times 10 to the 35th power, well, minus 35 power, meters is Planck length. That's about 10 to the minus 20th the diameter of a proton. Very small. Way beyond anything we can measure with any technologies we have, but finite. What if time, what if space is really consisted of pixels of this, like, instead of points of zero dimension pixels that actually have a size? How would we deal with fields like magnetic and electric fields and all sorts of fields in this? I don't know. What would a field look like in this kind of a system? I don't know. One of the great mysteries today in science is fields. What are fields? What's a gravitational field? For that matter, what's an electrical field? We have math models of them, and we can measure them. They exist. We've got experiments. We know. I mean, our whole modern technology is based on our current understanding of electrical or magnetic fields. Maxwell's equations, Einstein's equations, and even more things that we understand with the theories of relativity, which are actually different from quantum theory. And quantum theory and relativity theory contradict each other at certain levels. I mean, we have a real problem in physics today. The math models we have, in a certain sense, contradict each other. We have one set of math models we use for quantum theory, a different set of models we use for relativity theory. And they contradict each other at certain levels. It's a big problem today for physicists. So what I'm talking about here is very it's kind of theoretical. It's heuristics. It's just thinking, but we have problems today. In fact, how would this view affect our probabilistic view of quantum theory? In fact, maybe string theory is attacking this. I don't really understand string theory very well. Maybe you do. Does string theory use a new math? Maybe it does. Maybe it's using a math similar to what I'm talking about. I don't know. How about our concept of time? Is time continuous? Or are there discrete moments of time? Are we really living, if you think of like a TV program, it's a sequence of time. There's no continuous time. You show a frame, you wait, you show another frame, you wait, you show another frame, and you do that. And if you do it fast enough, our perception makes it look continuous. The same thing if you draw a line on a piece of paper. It's really a set of points interconnected. It's a very complicated thing, in fact. If you draw a line on a piece of paper with a pencil, that's not a theoretical line at all. That's a collection of points. It's a collection of atoms, a connection of molecules. The ideal concept of a line is it doesn't exist in reality. The idea that you have an infinite number of points between 0 and 1 on a straight line doesn't exist in reality. So our math is really deceiving us, I think, in many ways. We have very complicated mathematical structures. Let's take the exceptional Lie group, E8, which a lot of people are excited about today. They think it's going to help us come up with a better extension of the standard model in physics. Well, what would that look like in this kind of a number system? I don't know the answer. And indeed, can we just simply eliminate the concept of infinity, of an infinite set? Either an infinitely large set, or for that matter, that's for counting, or when you measure infinitely small things. Is there any such thing as a point that has zero area, zero size? Now, our number system could be a very large infinite set. And in fact, it could even be expanding. In fact, that's what the original finitists talked about. Is there such a thing as a set of all real numbers, or is it just a large infinite set that can be arbitrarily large as required? Now, Stephen Wolfram, who I consider one of the geniuses today, who's the developer of Mathematica and Wolfram Alpha and Wolfram Language, points out that there are many, many possible axiomatic mathematics systems. sapiens, that's you and me, our species, we've invented and explored a few of them. But as Steve Wolfram points out, there are many, 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 many more axiomatic systems that we have not invented or explored. And I use the word invented. Some people use the word discovered. Does an axiomatic system exist before it's invented? I don't know. I'll leave that to the philosophers. I think maybe just a question of semantics. But you can imagine another species, as Steve points out. Stefan, I should say. I shouldn't call him Steve. As Stefan points out, there could be another species that has a whole completely different axiomatic system that creates much, much better math models than ours does. Now, I must say, I realize that we sapiens tend to work together as tribes, and we share beliefs. And that's happened throughout history in all subjects, and particularly mathematics. And I'm talking about now what most mathematicians would consider a radically new axiomatic system. If it didn't include infinity, infinitely small numbers, it would be essentially a finite system. Probably most mathematicians today wouldn't take this seriously at all, because I'm not sure any current math tribe would consider this seriously. In the late 1800s, it was the other way around. I think a lot of mathematicians, as far as axiomatic systems went, really thought we needed to have finite systems, Kronecker being the example. Cantor came out with the infinity, and then you've got, as you watch my video on infinities, there's an infinite number of infinite sizes of infinity. But let me point out to you that our ancestors, sapiens, believed Euclidean geometry was the only geometry for a long time, centuries, many centuries, until a couple of centuries ago, which is really a pretty trivial amount of time, our ancestors discovered or invented non-Euclidean geometries. And those turned out to be much better for science math models than Euclidean geometry. Newton used Euclidean geometry, and he made physical systems. He made science math models out of them. Very good models, better than anything anyone had done to that time. He was able to, for example, with his math models, verify Kepler's laws of motion. That was the big thing he did, elliptical orbits. Now, there's a lot of things that he couldn't explain with his math model, and he knew it, but there were things he could explain that had not been explained before. It made the Copernican system now completely acceptable as a math model. But along came non-Euclidean geometry, and then Einstein created a much better math model than Newton's. As I pointed out in other videos, you wouldn't have GPS today if it wasn't for non-Euclidean geometry and Einstein math model. And I think, in a certain sense, the biggest problem that we've had with our math for creating scientific math models is this problem we've had with infinity. The Greeks really suffered from it when they discovered that if you demand exact precision in measurement, there are lines that do not have what is called a rational length. But we all know that in the real world we live in, that we perceive, that we can measure and that we are aware of, there's no infinite set of any kind of objects. There's a finite number of protons and atoms in the universe that we can measure and be aware of. And there's no arbitrarily small objects in the world we live in. We can't measure anything even near the Planck length. And that's 2 to the 20th times just for a proton diameter. Well, our axiomatic systems, ever since the Greeks, have assumed infinitely large sets, and because then they want to use, in a simple way, those sets to make measurements, they had to essentially assume infinitely small measurements with exact precision. That's what the Greeks did. When they assumed that there was infinitely precise measurements, and they took the right triangle with 2 sides 1, and they discovered the hypotenuse, was an irrational number. It was not commensurate with the unit length if you demand exact precision. And the Greeks reacted with something akin to horror. This really bothered them. They thought that was not possible. They thought any two straight lines were commensurate, which is another way of saying that there are no irrational numbers. And they actually retreated from the number concept. And numbers didn't get developed the way geometry did by the Greeks at all. Euclids Geometry doesn't say very much about numbers, really. Archimedes began to use numbers, and he even uses, I've said in other videos, infinitesimal numbers concepts. But it was not done axiomatically, it was done heuristically. And of course, suppose we considered ordered pairs in our plane, AB, pixels now. Well, then you might think of these pixels as being little circles, and they're all mixed together. And what would a line be that connected two pixels, capital A and capital B? Well, it could be a sequence of pixels from A to B, including A and B, that all touched each other. And we could call that a line. The problem is it's not unique, probably. Just draw pictures to see. There could be lots of other lines, that is, sets of pixels adjacent, connected A and B. So how will we even define then a line connecting A and B? Well, one way we could do it is we could take all these different lines and put them in one group and call that, I'll call it a capital line. It's kind of like equivalence classes in equivalence relations, just an idea. As I said earlier, all this needs to be treated axiomatically if it's going to become considered rigorous math. And we don't generally accept heuristic math until it's made rigorous. That's why they banned infinitesimals in the mid-1800s. They couldn't treat them rigorously axiomatically, so they banned them, although they were useful, very useful. Scientists and engineers kept on using them. And then in the 1960s, they're back in. We were able to treat them axiomatically, so now they're legitimate again. We're pretty, we tend to have a lot of hubris. We tend to think that what we know today is kind of like the ultimate thing, and that's truly nonsensical. Anybody that thinks that we somehow have arrived at some final math system, axiomatic system, and some final math model, now that person, in my opinion, is quite ignorant, meaning assuming things way beyond anything that's reasonable. We're nowhere near the end of that. And I don't know where the end is. There may not be an end to it. It may be that you can always find a new axiomatic system that will give you a better math model than the old ones you had. Just as Einstein's model based on non-Euclidean geometry was better than Newton's model based on Euclidean geometry. After all, human beings have only been creating and using math effectively for a few thousand years. And in the scheme of things, considering they say the Earth is 5 billion years old, that's not very long. So who knows? As I mentioned earlier, Kronecker in the 1800s really fought against this heading to this infinity thing that Cantor did. But Hilbert, then around the early 20th century, he endorsed Cantor's work, and this was a wonderful thing, and this is the way math should go. And math has gone mainstream. Today, infinity, irrational numbers, uncountable sets, all of that is standard math today. That's that our tribes today have. And I would say that modern math today, with infinity the way it is accepted by almost all modern mathematicians. I put almost all in quotes because almost all is kind of an inside joke for theoretical mathematicians. Let me give you an example. Almost all real numbers between 0 and 1 are irrational. Any mathematician knows what that means. In fact, if you set up measure theory and you take all the rational numbers between 0 and 1, now that's dense in 0 and 1. It's dense. Between any two real numbers, there's a rational number. But in measure theory, it has measure 0. So from a major theoretic viewpoint, the rational numbers are irrelevant. That's also true from a countability viewpoint. The set of rational numbers is what is called countable. That is, one-to-one corresponds with the natural numbers. The set of irrational numbers is uncountable, one-to-one correspondence with all the real numbers. That's a higher cardinal number, and that's the math we live with today. That's what our science models are based on. So the real question I'm asking is there an axiomatic system that we could invent or discover that would give us better science math models than we have today? Our science math models today are very good, especially compared to our ancestors. But there's lots and lots of things we don't know. We don't handle chaos well at all. We don't handle complex systems well. There's lots of things we don't handle. And of course, I obviously don't know the answer. I'm just a simple high school math teacher. Now, I was exposed to many of these modern infinity concepts because I did study math. As you know, I have a Ph.D. in math, algebraic number theory, and I've taught all these things. I've taught all the Cantor methods, the different sizes of infinity, and measure zero and unmeasurable sets and all sorts of things. I'm part of the tribe. If you're going to get a Ph.D., by the way, you got to be part of the tribe. And so I was. I guess I was a guest, I would say. I'm not more than a member. Anyway, this was just for food for thought. This is for something, if you're a young high school student, and remember all my stuff is kind of aimed at high school students, this is just something for you to think about and cogitate over. And who knows, maybe you can figure this out someday. Maybe you'll come up with a great axiomatic system that's far better than the ones we have now that would help us create better scientific models. That would be wonderful. Well, I wish you best wishes, and I close with the word supra, and that means beyond. After all, we've devised today, thanks to Steve Wolfram and a whole bunch of other people, the supercomputer, which does things that ordinary computers cannot do easily. It's very inexpensive, as you all know, and you ought to go look at it to see what it is. That's an idea of how our technologies evolve. Wolfram language today, for example, which is on the supercomputer, is far more powerful than any other programming language I'm aware of. Nothing to compare to even Python or Java. Is way beyond that. And that's the kind of thing you, as a high school student, should be learning. And, of course, you need to learn classical math because that's necessary to understand the current scientific models. But thanks to Wolfram Alpha, it's much easier to do today. You do not need to learn the old manual algorithms that are obsolete and very difficult and challenging to use and that often don't even work very well. You don't need to learn that. And that's all what my tiers 1 through 6 are all about, as you know from a lot of other things I've done. So this was just an idea to stimulate your thoughts. And so this is Dr. Dell, wishing you a wonderful life. See you on another video. Bye-bye.